Oh, hey, didn't see you there. My name is Ricardo Sanchez, and I'd like to talk to you about the chemistry behind saltwater fish tanks. Have you ever wondered what happens behind the seas of an aquarium? Well, lucky for you, my colleague and I have just the knowledge you want and are willing to share it. Let's get to it then. Oh, and that's Katya.
As you all may know, I have the best fish tank in town.
Why don't you show me, Katya?
Okay.
Now for a short commentary from the owner, Jerry Grossman.
Hi, my name is Jerry Grossman, professional musician, and one of my hobbies is taking care of my 120-gallon saltwater coral reef aquarium. I've had my reef aquarium for about 12 or 13 years, and at the moment there's only one fish in it, but I've got lots and lots and lots of soft corals, and a starfish, millions of snails, and hermit crabs, and critters, most of which I don't know the names of. A lot of fun. I do water changes about every 3 or 4 weeks. Do stuff with the filters underneath the tank. Keep the water chemistry up to snuff. That's mainly it.
I chose to research this topic for one reason, and that reason is justice. On a dark and stormy night, a tragedy occurred within my household. I was asleep, and so was my family. The power went out. When we awoke, we found that our fish had moved on to a better place.
You mean the freezer?
Here are 2 of the victims. They have been preserved in the family icebox and are waiting for their summer burial ritual. The real question is, what was the cause of my fish's death?
See, Katya, that wasn't really that much of a mystery.
What do you mean?
Well, the cause of death for Amy and the John was actually pretty basic. You see, they died from a lack of oxygen. And it all has to do with the basics of water chemistry.
Water chemistry is the most important aspect in keeping an aquarium in good condition. It controls almost everything inside the tank and directly influences the health of the specimens living inside of it. There are many specific parameters that need to be maintained in order for the fish and corals to stay alive in a saltwater aquarium.
In this video, we're going to cover
The role of individual elements and compounds in a saltwater aquarium,
the nitrogen cycle,
pH and alkalinity,
pH and GH of water.
and temperature and heat transfer. Natural seawater contains many elements that fish, algae, and invertebrates all utilize in their biological processes.
In a fish tank, some of these elements must be supplemented to keep the fish happy and healthy.
Let's start with one of the most essential elements in the fish tank, calcium.
Calcium is critical for the formation of many structures within the tank, including the skeletons and shells of corals and other organisms.
In artificial saltwater, the majority of calcium ions are free. However, about 10 to 15% are present as a neutral ion pair with sulfate, forming calcium sulfate. These types of soluble ion pairs are fleeting, forming and breaking apart very quickly. Calcium also makes bonds with carbonate and bicarbonate.
One important feature of calcium is that in seawater it is actually supersaturated. This means that under the right circumstances, it will precipitate a solid calcium carbonate that is insulated. Here's the equilibrium constant expression for the dissolution of calcium carbonate. When the product of the concentration of calcium and carbonate is greater than the KSP, the solution is supersaturated, and there's too much calcium and carbonate in the solution.
Precipitation will occur if the supersaturation is pushed to extremely high levels. This is caused by
A rise in pH,
a rise in temperature,
a rise in calcium or carbonate. We will talk more about calcium carbonate precipitation in relation to KH and pH later on.
Let's move on to phosphorus. The simplest form of phosphorus in reef tanks is inorganic orthophosphate. The structure of orthophosphate is a central phosphorus atom and 4 oxygen atoms arranged in a tetrahedron. Phosphorus can also take other inorganic forms, such as polyphosphate, which are rings and chains of phosphate ions strung together by phosphate, oxygen, and phosphate bonds. They form soluble compounds with calcium and magnesium, which softens the water and permits better cleaning action.
One source of phosphorus in fish tanks and seafood restaurant is typically 3% phosphate. Phosphate is oftentimes found in excess, and it causes the growth of undesirable algae and calcification.
Let's get some more information from Chris, the chemistry expert.
Hey, Chris.
Basically builds up in an aquarium over time. Most phosphate does not form from the aquarium. Most phosphate forms from the water you're dumping in the tank. So what you do is you pre-filter the water, and we do that with reverse osmosis. I take the water from the street and run it through a hydrogen filter, and then we run it through a carbon filter to fill it with chlorine, and then we run it through a reverse osmosis membrane, which pushes the water through, and that takes out about 90% of the phosphate. To get the last 10% of the inorganic phosphate out, it's very hard. So what we have is a cation and anion deionization resin bed, and it goes through that, and that pulls 99% of the last 1% of the phosphate out. Inorganic phosphate's very hard to take out of water. It bonds with the water very tight.
Iron can be supplemented in order to make a species of macroalgae grow faster and appear a more attractive green. This results in a better nutrient export system within the tank. Iron is unique in that it can exist in 2 ionic forms, iron 2 oxide and iron 3 oxide.
This allows iron to be used in ways that other metals cannot.
Iron is present in many types of proteins and organic molecules.
Now let's marvel at the redox reaction of iron.
Many applications of iron involve the use of its multiple oxidation states. For example, if you need electrons to complete a chemical transformation, you can begin with a bunch of iron 2+ that is bonded to a protein. When it contacts the molecule that you want to transfer the electrons to, it loses an electron and becomes iron 3+.
Iron is also critical for photosynthesis, which explains the substantial need for iron by phytoplankton and macroalgae in the aquarium.
The elements we have discussed so far all have benefits. However, not all compounds are beneficial to the health of the aquarium.
For example, the compound ammonia can enter the fish tank via the breakdown of waste and protein in the tank.
If the levels get just slightly above zero, all species can be endangered. Let's hear from Chris again. When the rate gets too high, the animals can no longer process oxygen, and they may start to die.
In addition to the elements we have already discussed, there are many more elements that typically exist in the saltwater fish tank.
Magnesium is responsible for the regulation of pH and the formation of invertebrate skeletons. Strontium is used in the development of skeletons and can increase the growth rates of hard corals and algae. Iodine is rapidly oxidized in the aquarium and is essential for the health of many soft corals. Boron works as the buffering agent and increases pH stability.
On to
The nitrogen cycle.
the nitrogen cycle plays a highly important role in that of close environments such as America. Due to its presence, it is possible to keep fish and small invertebrates alive in a small viral space.
The nitrogen cycle, also known as nitrification, is the 2 to 8 week cycle whereby ammonia is converted to nitrites and nitrites are converted to nitrates.
As we explained before, ammonia is a byproduct of the breakdown of waste within a fish tank. However, the ammonia produced does not usually harm the fish in the fish tank. This is because Nitrosomonas bacteria oxidizes the ammonia, thus eliminating it.
However, the byproduct of ammonia oxidation is nitrite, which is also highly toxic to fish.
At this point, Nitrobacter bacteria converts nitrites into nitrates. nitrates are not toxic to fish in low to moderate levels.
Let's have a summary of this cycle from Chris.
And those bacteria break down the ammonia into nitrite, and then nitrite now builds up in the aquarium. Now that gets broken down by another kind of bacteria, and that bacteria breaks it down to nitrates. Now nitrates go basically into the aquarium and they stay there. And there's two ways to remove them. You can remove them physically by purifying the water, the anion and cations, which can be used to remove it in filters. Then the third method is an anaerobic zone, which we have at the bottom of the aquarium, and that's the sand. The thick layer of sand in the lower part of the layer, you get anaerobic bacteria, and that's bacteria that can operate without oxygen, and that eats the nitrates. It's a much slower process. Fortunately, nitrates are much less toxic to the fish than the animals in the aquarium.
Let's talk about pH and alkalinity.
Aquatic organisms only thrive in a particular pH range. This range certainly varies from organism to organism, but the pH range from 7.8 to 8.5 is usually an acceptable range for reef aquaria.
Alkalinity is roughly defined as a measure of how much acid is needed to lower the pH to a specific level. Alkalinity or carbonate hardness are basically the same thing as alkalinity is measured in units kH.
Total alkalinity/reserve alkalinity can be defined as the amount of acid required to lower the pH of the sample to the point where all the bicarbonate and carbonate could be converted to carbonic acid.
GH is the general hardness in the tank. If water is hard, that means that it's full of minerals. Salt water is very hard. Generally, the bigger the pH, the bigger the G. Sum it up, Chris. Sum it up.
Basic pH scale, you've got acidity, alkalinity. These tanks run about 8.3, and then you've got, like I said, what they call reserve alkalinity, which is also called carbonate hardness. Not the general hardness of the water. It's not really a concern in the marine aquarium. You're more concerned with that reserve alkalinity, that fine balance, because it really is what the whole enchilada is built around, is that carbonate hardness and reserve alkalinity. Once you get that down to the right number, then the tank just runs itself. I mean, literally, the first year it took me to get it stable, and then now it's really a non-issue. It's got to get to a certain equilibrium, and then it'll stay there.
This graph shows the theoretical relationship between carbonate alkalinity and pH for seawater and freshwater equilibrated with the atmosphere.
As you were saying previously, one of the problems at a higher pH is the precipitation of calcium carbonate.
In order to prevent this, alkalinity levels must be suitably maintained. They can't be too low, inhibiting biological calcification, or too high, causing excessive abiotic precipitation.
Say it's 12 kH, there's a number, say. You got to keep that at a certain number. Now, if you keep it too high, if you keep the carbon hardness too high, none of the calcium will get absorbed. And what will happen is it'll start to snow in the tank. All the calcium, what they call precipitates, and it'll just all come out on the bottom. You'll see it look like snow all over the tank. It's basically supersaturated. You're supersaturated. So you've got to keep the carbonate hardness high enough to stabilize the pH.
Thank you for that, Chris.
Let's move on to our last topic, heat transfer. The major contributors to heat in a fish tank are lights, ambient temperature, and heat from the pumps.
Temperature can range from 72 to 80 degrees in a reef aquarium.
According to the first law of thermodynamics, heat is a form of energy that must be conserved. This means that the total amount of heat flowing into the aquarium must equal the heat flowing out plus the change in internal energy of the water.
For aquariums, this usually means that the heat from the lights and pump is balanced with cooling by the ambient room temperature.
This principle can be illustrated by a simplified concept of heat flow called Newton's law of cooling.
Newton's law of cooling states that the heat flow between an object and its surrounding environment can be characterized by a heat transfer coefficient, H.